Welcome my friends, welcome to my next lecture. Now this is week 6 lecture. So in my last lecture I discussed many nice theorems like Liouville's theorem, what is called then maximum modulus principle or maximum modulus theorem. Then we'll have Schwarz lemma. Then I have discussed what is called Morera's theorem. So couple of beautiful theorems I have discussed. And of course some of them used like what is called Cauchy's integral formula, some of them used what is called maximum modulus principle as a consequence. So these are the couple of beautiful theorems in complex analysis. Now for today's lecture my plan is to start the notions of what is called power series, because if you remember in my beginning of my lecture I said that analytic functions of course I have defined in certain way, but if I have the functions which is analytic, then suppose analytic say at a point z0. So I have already discussed what do I mean by analyticity at a point z0 and analyticity on an open set. So then you will see if I start with an analytic function which analytic say at a point z0, then you can have a power series expansions around that point. So but unless and otherwise you are not comfortable with power series, then how you can say that okay, if my function is analytic the way I have already defined the analyticity, then it will see that that functions will have a power series expansions and converse. If I have a power series expansions around the point z0, then that function has to be analytic. So that is why, so in some books in complex analysis they started with the definitions of analyticity at a point by saying that I'll say my function is analytic at a point z0 if and only if it will have a power series expansions around that point. Okay, so though I have defined in a different way, but later on when I'll talk about what is called notions of power series, then you will see both definitions coincide. Okay, so that's my plan for today's lecture. I'll start with the notions of power series. Of course, before that I'll start with couple of convergence of sequence, convergence of series, convergence of sequence of functions, series of functions, just couple of things you might familiar with in your real analysis concept. So I'll just recall those definitions, then I'll introduce what is called power series, then properties of power series, then you will have that famous power series representation of analytic functions, then Taylor series will come, which is the converse. That means if I have a analyticity it will have a power series expansions, and then you will have a Lorentz series. So let me see how far I can go, but for today's lecture I'll start with the notions of convergence and then I'll slowly introduce the concept of power series. Okay. So this is the learning outcome for this week lectures, this week 6 lectures. So what are the learning outcomes? So this is the, so as I said, I will just recall the concept of convergence of sequence of complex number and series of complex numbers, and then sequence and series of functions, because I need it. So you see, when I will talk about the notions of power series, then there are certain convergence I need to know, like pointwise convergence or uniform convergence. So I will just recall those things. So this is first two things are you might familiar with in your real analysis. Now this is the power series, again you might familiar with in real analysis as well, but I will talk about power series. I will introduce the notions of power series, then you will have a radius of convergence, then kind of properties of power series, that means sum, scalar multiplications, product, division, this kind of concepts I will talk about. Then you see if I have a sum functions or power series it will be analytic. Then the question is, does analytic functions have a power series representation? Answer is yes. Then it brings you what is called Taylor's theorem, very nice theorem. Then I will talk about analyticity, what do I mean by analyticity at point at infinity. Then two concepts, singular points, isolated and non-isolated, and at the end I will talk about what is called Lorentz theorem or Lorentz series. So that's the full plan for this week lectures. Okay, so let me just start with the concept of convergence of sequence of real numbers. Now what is the sequence of real numbers? If you know the definitions of sequence, that means it should be a map from set of natural numbers to R or C, whether I am talking about sequence of complex number or sequence of real numbers. So I have given, so a sequence of complex number is a map from set of all natural numbers to C. That means for n is in natural number capital N, then I am saying that the value of A at n is nothing but A suffix n. So that means sometimes I am saying that this is my sequence. So that means n goes to A suffix n. So this kind of map. Okay. So sequence definition is perfectly all right. So in sometimes I am written that second bracket n or first bracket or maybe this kind of notation. So these are the kind of different books have different sort of notation. So this is the notation of sequence. Now what is the meaning of convergence? So if I have a sequence of complex number and I'll say that the sequence n, that sequence of complex number converges to some point and I say a naught at some, this is what I have written, a star. So S2 A star at 2 A star in some other complex number. What is the meaning? So meaning like in the real convergence of real sequences that you know, that means the distance between the sequence term and the limit should be very small if n is large enough. So that's the meaning. That means I can make the distance between terms of the sequences and the limit should be very small. That's the idea. So but to have or to write those concepts mathematically, that means since we have the notions of distance in complex number, so instead of absolute of real number, now since I am dealing with complex sequences, so in complex sequences what is the corresponding distance? Distance of the or absolute of the complex number. So you just replace your distance concept of modulus in real number to modulus of complex numbers. Okay, so that's what I have written. So let n be a sequence of complex numbers, that is I have already given the definitions. If there exists a complex number A star which satisfies the following properties, what is that? That means given epsilon I should have a natural number n naught such that the distance between n and A star I can make it very small whenever n is large enough. So that means you can say that the tail of the sequences n minus A star is very small. So that is the like definitions you are you comfortably in real analysis. Same definition, just the corresponding modulus of real number should be replaced by modulus of the complex number, since I am dealing with convergence of sequence of complex number this time. Okay, so given epsilon I should have a natural number n naught such that the distance between n minus A star is less than epsilon for all n greater or equal to n naught. If these things happen for a given sequence n and for a point A star, then I will say that my sequence n converges to A star. A star is called the limit of the sequences. This is the abbreviations I can write, n converges to A star as n approaches to infinity, or maybe this is the kind of symbol. Limit n approaches to infinity, n is equal to A star. So two examples I have given, very easy examples. So first sequence is that, so your sequence is n. What is my n? My n is 1 by n plus twice I. Now this is also, you can easily say that why it will converge. Now if n approaches to infinity, suppose this is converges to something as n approaches to infinity. Now look, if n approaches to infinity, where this 1 by n sequence converges to 0 and 2i is a constant, it will keep aside, keep it as same. So therefore this is converges to 0 plus 2i, which is exactly equal to 2i. Standard, you know the convergence, right? This is converges to 2i. And what about this one? This one you can check it, but one has to prove it. Now, prove means what? If you know the convergence of your sequences, then it will be okay. So what is that sequences n? In fact, well, there is a theorem you can have it, because you see this sequence, anyhow, I think I will talk about that, it will be clear. So consider the second example. What is that? So you have a sequence n, right? So let me just remove this portion, it will okay. Okay, so now consider this sequence an. Second example, think about second example. What is that? This is n to the power 1 by n plus I times n plus 1 by n. Right? Now n is a complex number, so I can think about that n is equal to bn plus ICN, where bn is real, cn is real. So therefore this is the bn part and this is the cn part. Right? Now look, so now given sequence n of complex number, it will generate two sequences. One is bn, another is cn, and both are real sequences. Now one can prove that if my complex sequence n, if it converges and if I write n is equal to bn plus ICN, then the corresponding generated sequences, that means the sequence bn coming from sequence n, so this is coming from here, this is also coming from here, so corresponding bn sequence converges and cn sequence converges. And conversely also true. That means if I have two real sequences bn and cn both converges, then if I construct a new sequence n of complex number which is bn plus ICN, then n sequence converges. So this is if and only. Now you see, so I want to know the convergence of the sequence n which is of the form bn plus ICN. Now if I use that kind of observation, that means it is enough to talk about the limit of the sequence n, it is enough to talk about the limit of its individual sequences, that means bn and cn. Now you see, bn what kind of sequence? This is actually n to the power 1 by n. Now you know limit n approaches to infinity bn, that means limit n approaches to infinity n to the power 1 by n. Why it will converge? From your real analysis knowledge you can say that this is converges to 1. Okay, so you just check it, this is okay. And what about limit of n approaches to cn, which is limit n approaches to infinity 1 plus 1 by n, right? And what is that? Very simple, this is converges to 1. So therefore, this is converges to n converges to limit of Bn plus I times limit of Cn. So that means it will converges to 1 plus I times 1, that means 1 plus I. That's what it is. Okay. So that's why you can prove it. Okay. So it is if and only. So given a complex sequence n, if I write n is Bn plus ICn, then the corresponding, if n converges, the complex sequence converges to some point, say A star, and suppose if I write A star as, say, A1 star plus I times A1 double star, where A1 star is the real part and A1 double star is the imaginary part, then I can say that if I write n as Bn plus ICn, then the corresponding sequence Bn converges to A1 star, and the sequence Cn converges to A1 double star. Okay. So these are the results, couple of properties. In fact, I have written those results. You see that this is last one. If n, if I write as xn plus iyn, and suppose it converges to the point A star, which is x star plus iy star, if and only if the corresponding real sequences xn converges to x star, yn converges to y star, if and only. So that means if n converges to A star, then the corresponding generated sequence xn and yn, which is converges to x star and y star respectively, where x star is a real part of A star and y star is a imaginary part of A star. And if I start with xn, which converges to x star, yn converges to y star, and if I add it xn plus yn, if I say that this is another sequence n, complex sequence, which converges to A star, what is my A star? Which is limit of the sequence xn plus I times limit of the sequence yn. Okay. So therefore, this is the same as n converges to A star if and only if the corresponding real part of the sequence is n converges to real part of A star, and imaginary part of the sequence n converges to imaginary part of A star. So this is a nice properties, because in some point of time, if you would like to find a limit of some complex sequences, so it is enough to break up into two real sequences, or break up into write into xn plus iyn and get the limit of xn and yn. Okay, so like, and the kind of couple of properties that you are comfortable or that you are familiar with, what is called real analysis, all kind of results are true in case of complexes. It says that if n converges, then the limit is unique. I am not going to prove it, this is straightforward. If n converges, then the set S is bounded. If n converges, then the modulus of the sequence, which becomes a sequence of positive real numbers, that converges, but converse is not true. That means it says that if n converges to A star, then it will implies that modulus of n, that sequence, it actually converges to modulus of A star. I can prove it. Why? Because you see, n converges to A star means what? That means n minus A star, that is goes to 0 as n approaches to infinity, right? So my claim is that if this is true, this will implies. Now that you can prove it, right? Because modulus of n means what? It's a positive real numbers, right? And modulus of A star, that is also positive. So therefore you can just estimate modulus of mod n minus mod A star. What is that? This is by inequality, I have already proved it. This is dominated by modulus of n minus A star. Because of all n and A star are complex numbers. So that means I am using that fact. Modulus of mod z1 minus mod z2, which is dominated by modulus of z1 minus z2. So this is the fact. Now you see this is converges to 0 as n approaches to infinity. So therefore this will implies mod an converges to mod A star. So therefore if n converges, then modulus n converges. But converse is not true. But that kind of examples you are already familiar with. Why? You can easily give that modulus of n converges while n is not converges. You can easily see. So consider the sequence n is equal to minus 1 to the power n. Okay. Though I am saying this is a real sequence, but that same real sequence I can think about as a complex sequence, right? So what is this n? This what kind of sequence? This is a minus 1 plus 1, minus 1 plus 1. It is actually oscillating sequence, it is not converging. But if I take the modulus of n, you consider this sequence, what kind of sequence? This would be modulus of minus 1 to the power n. And what is that? This is actually a constant sequence 1, 1, 1, 1, 1, and this converges to 1. So therefore n converges implies modulus of n converges, but the converse is not true. This is the one simple example. There are plenty. Because the corresponding the example you know in your real analysis, same example will work, because real analysis or real sequence is nothing but a complex sequence. I'm just thinking that imaginary part is 0. That's it. Okay. Now come to the series of complex numbers. You know the convergence of series of real numbers. So same definitions I can cope up into what is called series of complex numbers, because if I have a series of complex number, take a sequence of partial sum, then it is a sequence of complex number, and I already discussed what is the meaning of convergence of sequence of complex number. So that's it. So now if I have the sum n from 0 to infinity in a0 plus a1 plus a2, it's called infinite series of complex numbers. Definition of convergence: suppose this is a series of complex number, define sequence of partial sum starting with s0 is equal to a0, sn is equal to k from 0 to n ak. So this is a sequence of partial sums. Now if there existed a complex number s such that this sequence, now what is the sequence Sn? Because since this is a finite number, so if I add it, it will give you some complex number, because it a0, a1, a2 up to n is a complex number, sum is also a complex number. So therefore this sequence is a sequence of complex number. So if that sequence converges to some complex number s, that means sequence of partial sum converges, then I will say that series, my series converges to S, and I will write sum over n from 0 to infinity n is exactly equal to S. So this is like the convergence of series of real numbers. You know, you just replace by real by complex, same definition will work, just you have to be little bit careful here. Instead of modulus of real numbers, I'm dealing with modulus of complex number that I already discussed in my earlier lectures. So that's it. So now you have the convergence of series of complex number, it is done. Couple of examples. So if the sequence of partial sum does not converge, then I will say that my series diverges, actually it not converges. Okay. Or not converge, so that means it should diverge, fine, that's perfectly alright, I will say that. Now a couple of examples I have given. For example, same thing. So like if I take this n, which is 1 by n square plus I times 1 by 2 to the power n, then I am saying that this summation 1 by n converges. Why? You can easily check it. What is summation 1 n from say 1 to infinity? What is that? N from 1 to infinity. So this should be 1 by n square plus I times 1 by 2 to the n, right? So now you will see that this individual 1 by n square, n from 1 to infinity, this is a convergent series, and similarly n from 1 to infinity 1 by 2 to the n, that is also convergent series. So therefore this is convergent, this is convergent, so therefore this is convergent. You cannot say that less than infinity, because you see, so at the end the sum of the series will give you a complex number, right? So therefore this does not make any sense. The convergence means the corresponding sequence of partial sum will converge. That's what the meaning. Okay. Similarly, if I take this sequence 1 by factorial n, 1 by 2 to n, now you see this is also convergent again, because I can break up into two parts. So one is 1 by n factorial and another is 1 by 2 to the n. 1 by n factorial converges to e, 1 by 2 to the n converges to 2, so therefore it is done. What about this one? This is diverges. Why? Because even though this 1 by 2 to the power n, that sum is converges, but sum over 1 by n, actually this diverges. Okay. So therefore you can say that, well, sir, if I have n which is bn plus icn, what is the relation of the convergence of n and convergence of bn and convergence of cn? So what I observed is that if your sequence series n, where n is of the form bn plus icn, if this summation bn and summation cn converges, it will imply the convergence of some n. That's what it is. And if one of them diverges, then your sequence diverges, and that's what exactly I have done it. Okay, so this is the one. So okay, so this is the kind of couple of examples. So first one converges, second one also converges, but third one actually diverges. Okay, that is fine. Okay, so maybe you can prove it. Okay, so maybe you can think about that. What will be the relations of the convergence of an and convergence of bn and cn? So one way is that if sum over bn and sum over cn it converges, then it will converge. Then sum of n is convergent. That is perfectly all right. Then you can prove that if sum n is convergent, then whether this sum bn and sum cn convergent. Answer is yes, you can prove it. Why? Again, just you use the what is called definition. So that means if, let me just try it, if sum n converges, right? So that means what does it mean? That is converges to sum say a. Okay, what does it mean? That is if and only the corresponding Sn, the sequence of partial sum, that is converges to my a, right? Now you have a sequence of partial sum Sn. So this is converges to if and only if I write Sn as say two parts Sn star plus say I times Sn double star, which converges to a, that means a1 plus ia2. This is if and only my sequence Sn star converges to a1 and Sn double star converges to A2, right? But you see, if I have a sequence of partial sum Sn, then what is Sn star and Sn double star? You just check it that Sn star, this is a sequence of partial sum of this sequence sum over Bn. And check that Sn double star, that is also a sequence of a partial sum of my series Cn. Now, since sequence of partial sum converges to A and sequence of partial sum converges to A2, so therefore the sum is convergent and therefore you will have the result, and similarly vice versa. So therefore, if sum of An converges, and if I write An is equal to Bn plus I times Cn, then sum over Bn and sum over Cn both real series converges. Conversely, if sum over Bn and sum over Cn converges, then if I consider a new series of complex number, that means sum over An, where An is equal to Bn plus I Cn, then the corresponding series also converges. It just follows from the definitions of the convergence of series of complex number. That's it. Okay. So you just complete in your home. Okay. So another definition is that, like in the real case, when I will say that my series sum over N converges absolutely, if I take the absolute of my complex number and if I consider this positive term series, if this converges, then I will say that my series converges absolutely. So couple of results. So if An converges, then like in the real case, you know, if series converges, then the nth term goes to 0. Here also this is true. If An converges, then the nth term goes to 0. Now, if An converges absolutely, then it will imply what is called N, the normal series of real numbers, the complex number that converges, if it converges absolutely. But converse is not true. Like in the real also, you know, na? For example, yeah, for example, this is the thing, that means what it says is that sum N finite implies sum N converges, but converse is not true. That means you will have the convergence of N but not. So what is the corresponding counter example? You consider this series, na? You consider N is equal to minus 1 to the power N, so alternating sequence, na? Minus 1 to the power N by N. If I consider this sequence, then what is the corresponding series? This series N from 1 up to infinity minus 1 to the power N by N. But what is this series? This is actually alternating series. That means it should start from 1 minus half plus 1/3, so on so. And this is convergent, right, by Leibniz rule, you know. Okay. But if I take the absolute of this sequence, that means if I consider this sum over mod N, what is that? Sum over 1 by N. And that is actually infinity, diverges. So therefore, absolute convergence implies ordinary convergence, but ordinary convergence need not imply what is called absolute convergence. That's what it is. If N converges absolutely, then summation N converges, but the converse is not true. Okay. Similarly, we can define. Okay. So this two concepts I have defined for sequence of real numbers and sequence of complex number and series of complex number. Same set of definitions you are comfortable with real analysis, just the corresponding modulus of complex number replaced by modulus of the modulus of the real number is I replace by modulus of complex number. Same way, like the concept of what is called sequence of complex sequence of what is called real functions and series of real functions. If you know the pointwise convergence and uniform convergence in real analysis, those kind of concept I can also bring in the context of complex functions. So that's what I have written. Similarly, we can define sequence of complex function and series of complex function. Now I have defined sequence of numbers, complex numbers and series of complex numbers. Now instead of numbers, I will deal with functions. If I have a sequence N, if N is a complex number, this is a sequence of complex numbers. Now, if I say that N is a function, complex functions, then this is a sequence of complex functions. And in the series sum over N, if N is complex number, then I will say that it is a series of complex number. But if I replace N by complex function, then it is a series of complex functions. So I can define it. So that is the kind of sequence of functions. So once I have a sequence of functions, then two types of convergence will be there. One is pointwise convergence, another will be what is called uniform convergence. Let me just first define what do I mean by sequence of functions. That means this time it is actually a sequence, just I am replacing N by functions. That's it, nothing else. So what is the definition? Definition is that let Fn be a functions from some domain D subset of C to C be a functions defined on a set D. We say that the sequence Fn, you see now this time actually An is replaced by Fn, or Fn is a functions of functions. So this is called sequence of functions Fn. So Oh, well, I'm talking about the pointwise convergence. So now I have a sequence of functions fn. So now two types of convergence will be there. One is pointwise convergence, another is uniform convergence. Now since I am dealing with functions, right, so that means this sequence is same as this sequence, same thing, it's a functions, right? Now what it says is that, you see, since each fn is a function, so if I take a point z0 is in D, fixed point, and if I consider this sequence fn of z0, then what is this? This is actually given sequence of functions. If I fix a point z0, then this is the corresponding numerical sequence of complex numbers, and that convergence I have already discussed in my earlier slides. So therefore this convergence you know. So therefore what I am trying to say is that given a sequence of functions which is nothing but each element is a function, if I fix a point z0 in the domain of my functions fn, if I consider this numerical sequence, if it converges, then I will say that my sequence, and if it converges for each z0 in D, if this is the case, then I will say that my sequence of functions fn converges to what is called pointwise. But you have to be a little bit careful. You see, if I fix z0, then I will have one sequence. Suppose it converges to a suffix z0, some complex number. Now if you see, if I change my z0 to z1, if I consider this sequence fn z1, this is also a numerical sequence, this is also a sequence of complex number, but this could be different from this one because I am changing my point. So therefore if it converges, suppose let it be a z1, suppose this is also converges. Now if I continue like that, so that means if I consider fn z, where z is some point in D, fixed but arbitrary, and suppose it converges to a point az in complex number, and this is true for each z, then I will say that my functions, sequence of functions fn converges pointwise. But you have to be careful, if I change my point, the corresponding numerical sequence changes, so therefore the corresponding limit might change. In fact, limit could change, okay. And if these things happen, then I will say that my sequence of functions fn converges pointwise. That's exactly I have written. So let fn be a functions defined on a set D. We say that the sequence fnz of functions converges pointwise. Pointwise means what? I fix a point, consider the numerical sequence, and it converges. So therefore converges pointwise. Okay, so then you say that if it converges means what? For each point z in D. So then what I am saying is that now define a functions from D to C such that f of z is equal to a suffix z. So it will give you a functions now. So if the corresponding, if I fix a z, fixed but arbitrary in D, if I consider this numerical sequence, suppose it converges to some point a suffix z, because the sequences depends on z. If I change z, then another different sequence will come. So that means the corresponding limit will be different. So that is why I am defining the limit a which depends on z. So I am saying a suffix z. Now if I define a functions f from D to C such that z goes to a suffix z, then I am saying that this sequence fnz, if it converges to functions f of z for each z, then I am saying that my functions, sequence of functions fn converges pointwise. So that is the definitions. So say suppose we have functions defined on a set D, we say that the sequence fnz of functions converges pointwise to a functions f. I can have a functions if, look, for each z0, the corresponding numerical sequence should converges to f of z0. So therefore for given for each point z0, or for each epsilon, there exists a natural number n0. Now this time n0 depends on both what? Epsilon and the point z0, because if I change the point z0, my sequence are changing. So therefore given epsilon, I should have a n0 which should depends on epsilon as well as z0. So that is important, such that this should be true. And if this is the case, then I am saying that my sequence converges pointwise, and this is the notation, limit n approaches to infinity, fnz is equal to fz for z is in D. Okay, so this is clear, I hope. So therefore suppose you have a sequence of functions fn, I will say that my sequence of functions fn converges pointwise to a functions f if and only given epsilon I should, or first you fix a point z0, then given epsilon you should have the existence of one n naught which depends both on epsilon and the point z0 such that this is true. And that means, in other words, what I am trying to say is that fix a point z0 in D, the corresponding numerical sequence fn z0 should converges to f of z0. That's it, that's the meaning. And epsilon delta, if I do it, because given epsilon, that n0 I am getting, it should depends both on epsilon and the point z0. Of course n0 will depends on epsilon, because that's the definition of convergence of sequence of complex number. But why it depending on the point z0? Because if I change z0, the corresponding numerical sequence fn z0, that also changes. That is why the n0 you will get, it depends both epsilon and z0, such that this difference should be less than epsilon. That means for fixed z0, the corresponding numerical sequence fn z0 converges to f z0. If these things happen for each z0 in D, then I am saying that my sequence fn converges to f pointwise, and this is the corresponding notations. Now, why I am writing n0 depends on both epsilon and z0? Because you see, I am talking about pointwise convergence. So another convergence will be there, that is called uniform convergence. Now, to have the uniform convergence or to distinguish uniform convergence from pointwise convergence, this n0 is very important. Now, for pointwise convergence, given epsilon, you can have the existence of n0 which depends both epsilon and z0 such that this equation is true. That means fn z0 minus f of z0, fn z0 minus f of z0, I can make this distance less than epsilon whenever for all n is greater or equal to n0. But you see, when I will talk about the uniform convergence, I will say that, well, I will say that the sequence of functions fn converges to f uniformly if given epsilon there exists a n0 which depends only on epsilon and not on the point z0 such that this is true. That means I will say that given epsilon there exists a n0 such that fn z0 minus f of z0 less than epsilon for all n greater or equal to n0 which depends only on epsilon, and this should be true for all z0 in D. If these things happen, then I am saying that this converges uniformly. That is why, so to have a distinction or to get an understanding or to get a difference between the pointwise convergence and uniform convergence, it is better to write given epsilon and a point z0, your n0 depends on the point on epsilon as well as point z0. That is important. Okay, so then I am saying something, if for some point z0, if the corresponding sequence does not converge or tends to infinity, then I will say that this sequence fnz diverges at the point z0. This is standard. Okay, so one example I am saying, what is that? If I consider this sequence of functions fn z is equal to z to the power n, where z runs over open unit disk, then I say that I am saying that, okay, consider the function f of z is equal to 0, then this sequence fn z converges pointwise to f of z, and that you can easily prove it. Why? Because you see, so maybe I should write n0, you see, depends on epsilon as well as point z0. Now what is this? So you have the sequence like z to the power n, right? N from 1 up to infinity, where, or maybe this is same as fn z, okay, where fn is a map from D to C, where D is an open unit disk. That means z, I am considering z goes to z to the power n, and what is my D? This is all those z in C such that mod z is strictly less than 1. That is very important. Okay. Now you see this converges to, it's saying that f of z is equal to 0 for all z in D pointwise. So what you do, fix a point z0. So I am fixing z0 in D, where D is the open unit disk, right? So that means all those z in C such that mod z is strictly less than 1, right? Now consider the numerical sequence. That means consider the sequence fn at the point z0. What is that? This sequence is z0 to the power n, and I am saying that this will converges to 0. Why? Because you see, z0 to the power n. Now you see, if n converges, I already proved, if n converges, then what? Modulus of n also converges. I have already proved it. No? This one prove, yeah. See, n converges, modulus of n also converges, right? So hold on. Okay, so okay, anyhow, one can prove it, doesn't matter. So I want to show that z0 to the power n converges to 0. So what I have to do, I have to estimate. So that means z0 to the power n minus 0, which is same as z0 to the power n absolute, which is same as mod z0 to the power n, right? Now what is mod of z0? Z0 is in D, so therefore modulus of z0 is strictly less than 1. Now since this is strictly less than 1 and you have mod z0 to the power n, now if n approaches to infinity, how it will go? Straightforward, it goes to 0, n approaches to infinity. Because modulus of z0 is strictly less than 1. And this is true for all z0 in D, so therefore you can say that this sequence fnz, this sequence fnz, which converges to f of z is equal to 0 pointwise. Right? Because if I fix a z0, if I consider the numerical sequence z0 to the power n, because of the fact that modulus of z0 is strictly less than 1, so therefore this is converges to 0 as n approaches to infinity, and hence z0 to the power n converges to 0, and since z0 is arbitrary, which implies that fnz, or you can say that z to the power n converges to 0 functions pointwise, and that's exactly I have written. So therefore fn converges to f of z, where f of z is equal to 0, it converges pointwise. So this is the pointwise convergence. So pointwise means given a sequence of functions, fix a point, and if my numerical sequence fn of z, that fixed sequence converges for each z, then the limiting functions, let it be f of z, then I will say that fn converges to f pointwise. Okay, so once I have a pointwise convergence, then series of functions, I can talk about pointwise convergence, because if I have a series of functions, then I will come to the what is called sequence of partial sum. Now sequence of partial sum, it becomes a sequence of functions, and sequence of functions I already talked about pointwise convergence. If the sequence of partial sums of my series of functions converges pointwise, then I will say that my series converges pointwise. So like series of real numbers, a series of complex number and sequence of complex number. So this is the series of functions pointwise convergence. What does it mean? Look, let fn be a functions from some domain D subset of C to C, n from 0, 1 up to with the functions. The series, you can have this series. Now what is the meaning of convergence of series? You go to the convergence of the sequence of partial sums. Now if I take a sequence of partial sum, so this is my sequence of partial sum Sn z, which is k from 1 up to n. Now since it is a finite sum, each Sn is a function, so each Sn is a function from D subset of C to C. So therefore now from the series of complex function to I am reducing to the sequence of complex function, and now sequence of complex function, that convergence, pointwise convergence, I have already discussed. So therefore I am saying that this series converges pointwise to a function s of z if the corresponding sequence of partial sum, which is actually sequence of functions, if it converges pointwise to a function s of z. So therefore, to talk about the pointwise convergence of a series of functions, you come back, or you do, or you first you go to the what is called sequence of partial sums of this series of functions. That sequence of partial sums of the series of functions will give you a sequence of functions, and sequence of functions, if it converges pointwise to some functions s of z, then I will say that my series fnz converges to s of z, that is the sum functions pointwise. So that's the meaning. In this case, I will write s of z is equal to n from 0 to infinity fn of z, and this is pointwise. Pointwise means you go to the sequence of partial sum, have a sequence of functions there, and if that sequence converges pointwise, that's it. One simple example I have discussed, that is like fn of z to the power n. So well, that sequence of functions fn z, which is z to the power n, and this function depend on open unit disk. So while it converges, sequence of function pointwise converges to 0, that I already proved. Now I am considering the same functions fn, but this time I am talking about this series fnz. So say n from where to where? N from 0 to infinity. So that means n from 0 to infinity z to the power n. Now I am asking where it will converge. This series also will converge pointwise, and what will be the pointwise limit? Pointwise limit should be, I think this should be 1 by 1 minus z. Why is that? Because you see, you can have it, you can prove it, right? For example, you just get the sequence of partial sum. What is the sequence of partial sums of here? So what is your Sn? Sn, actually you can say that this is k from 0 to n, what is called z to the power k. What is that? 1 plus z square up to what? So you can write it, this is 1 plus z square up to z to the power n, right? Sn of z, you can write Sn of z. But what is z? Z actually coming from what? D, and D is open unit disk, right? Mod z is less than 1. So therefore you can see, I can write this object by geometric sums, right? So that means you can say that this is actually 1 minus z to the power, well, I think this should be 1 minus, yeah, so this should be 1 minus z to the power n divided by 1 minus z, I think. This is the object. Okay? So you just calculate it. I think, yeah, okay. I think this is true. Right, this is true. So that means this sequence of partial sum, you can write 1 minus z to the n divided by 1 minus z. Okay, so this is the sequence of partial sum. Now to talk about the pointwise convergence of this series, you have to go to the sequence of partial sum. And if I take the sequence of partial sum, which is nothing but k from 0 to n, z to the power k, which is 1 plus z square divided by 1 up to z to the power n, right? So now what is that? This is nothing but 1 minus z to the n divided by 1 minus z. Now if I want to say that this sequence of partial sum converges pointwise to something, then I will say that that series converges pointwise to that sum functions. Now look, so I have, this is the sequence of partial sum. Now if n approaches to infinity, why it will converge? Now if see z is in D, right? since z is in D, mod z is less than 1. So therefore z to the power n always goes to 0. That is true. Now, so therefore if n approaches to infinity, so look what will happen. So the numerator z to the power n goes to 0, so this will go to 1 by 1 minus z. So therefore the corresponding sequence of partial sum converges to 1 by 1 minus z. So therefore the series of functions, it converges pointwise to the functions 1 by 1 minus z. So that's what exactly I have written. So you can prove it, okay. So that means there is nothing complicacy in that concept. If you know the concept of convergence or say pointwise convergence of sequence of complex function, then you can easily talk about the pointwise convergence of series of complex functions. What you have to do, instead of dealing with the series, what you do, you come back to the sequence of partial sums of this series. Now if I have a series of functions, if I come back to the sequence of partial sum, then it becomes a sequence of functions, complex functions, and I know the, if I know the pointwise convergence of this sequence of partial sum functions, then I can talk about what is called the pointwise convergence of my series of functions. So same thing, I am giving very simple examples. For the sequence of functions, I am considering f n z is equal to z to the power n, and for the series of also f n z is equal to z to the power n, but you have to be careful, this time z actually running over the open unit disk, then life will be easy to calculate or conclude something. Okay, so this is all about pointwise convergence. Now you see absolute convergence, that is like the absolute convergence of complex sequences, you know. So if I have a functions fn, of course starting with some functions, we say that the sequence of functions fn j converges absolutely to a function g. So instead of dealing with the functions fn j, now I will start with the functions what is called modulus of fn j, this kind of functions. So that means you start with the new function, define a function g and z which is absolute of fn j, okay. This is the function, new function, and talk about the convergence of these sequences. If these sequences converges pointwise, then I will say that my corresponding sequences fn converges absolutely pointwise. So that's what I have written. So we say that a sequence fn z, which is a sequence of functions, converges absolutely to a function g of z if for each z naught the corresponding sequence absolute of fn of z naught converges pointwise to g of z naught. So therefore, to talk about the absolute convergence, instead of dealing with the sequence fn z, you deal with the sequence absolute of fn z. Like the absolute convergence of sequence of complex number. What is the definitions? A sequence n of complex number which converges absolutely if the corresponding modulus of n converges. So same thing. Instead of dealing with the sequence fn, you should deal with the sequence modulus of fn of z. If this is converges pointwise, then I will say that my sequence fn converges absolutely. Okay, so that's what it is, the sequence converges pointwise. This is for the sequence. Series also same thing. If I have a series, go back to the sequence of partial sum, okay, it will give you a sequence of complex functions. If that sequence of complex function converges absolutely, then I am saying that my corresponding series of functions converges absolutely. Same thing. If the series converges absolutely to a functions tz, if the corresponding sequence of partial sum, what is the sequence of partial sum? Now you see, instead of dealing with the series fn, you have to deal with this series fn of z. So what is the corresponding sequence of partial sum here? So this is the corresponding sequence of partial sum. Na? So that's it. So instead of dealing with the series fn, now you should deal with the series sum of absolute of fn of z. Consider the sequence of partial sum. If it converges pointwise to a function t of z, then I will say that my series sum over n from 0 to infinity fn, which actually converges absolutely to a function tz. Okay. So okay. So yeah. So maybe one more uniform convergence. Let me discuss. So let fn from the subset of C to C be a functions. So as I said, what is the meaning, what is the difference between pointwise convergence and uniform convergence? So for the pointwise convergence, given epsilon and a point z naught, the corresponding numerical sequence fn z naught should converges to f of z naught, or in other words, given epsilon, I should have the existence of n naught which depends on epsilon as well as point z naught, such that fn z minus f of fn z naught minus f of z naught, I can make this is less than epsilon, and that should true for all n greater equal to n naught. N naught depends on epsilon and z naught. Now as I said that time, so if I given epsilon, if I have a n which depends only on epsilon and not on the points, then I will say that this convergence is uniform, and that exactly the definitions. So we say that the sequence fn of functions converges uniformly to a functions f in the set D if given epsilon there exists a natural number n that may depend only on epsilon. As I said, it should not depend on the point. That is why the term uniform is there. It should not depend on the point. It should depend only on epsilon, such that fnz minus fz, which is less than epsilon, for all n greater or equal to n, and this is the main part. It should true for all z. When I was talking about pointwise convergence, I am saying that fixed z naught. That means this n depend on epsilon as well as z naught. But to talk about uniform convergence, same definition will work, but this time you have the capital N which depends only on epsilon and not on the point. So that fnz minus fz less than epsilon for all n greater or equal to n, and this is true for all z in D. If this is true, then I will say that my sequence of functions fn converges to the functions f uniformly. Then what will be the convergence, uniform convergence of series of functions? Same thing. You have, if I have a series of functions, then you go back to the, or you write a sequence of partial sum of this series of functions, and if that sequence of partial sum, if it converges to some functions sz, say uniformly, then I will say that my series of functions converges uniformly. That's it. Okay, that's what I have written. Definition: the series this converges uniformly to a functions s. Come back to what is called corresponding sequence of partial sum, which is a sequence of complex function. If this sequence of partial sum converges uniformly to my functions s. If this is true, then I will say that my series of functions converges uniformly to the function s. Okay. So this is like I think one theorem I should say. This is some sufficient conditions, right? So like, when I say that given a sequence of functions or say series of functions, if I have a series of functions, when I can say that that series of functions converges uniformly. I think similar kind of theorem you might familiar with in your real analysis as well. So when you dealt with what is called sequence of real functions or series of real functions, that is called Wester's M test. What is that? Suppose you have a Mn is a sequence of non-negative real numbers. Start with a sequence of functions fn with the fact that fnz is dominated by mn, and this is true for all z. That means you can have the existence of m suffix n such that this is true, fnz is lesser or equal to mn for all z, with the fact that if sum over mn converges, then I will say that this series of functions fnz converges uniformly, and it also converges absolutely. So uniform convergence implies also absolute convergence as well. Okay, but in this setting, of course. One of the simple example is that, maybe in my next class I will do that this series, if I consider n from 1 up to infinity Zn, which converges uniformly, but you see what disk I am considering. I am saying that you consider a disk of radius r, but r is actually less than 1. I am not saying it is open unit disk. I am saying that you have an open unit disk, but you take a small disk where r is less than 1. Here my sequence sum over Zn, what is called, converges uniformly. Okay, so this is maybe in my next class I will do that. And then there is a useful result, like for example, if I have a sequence of functions, and suppose sequence of functions converges uniformly to your functions, and if suppose each sequence of functions are say continuous functions, can I say that my function is continuous? Limit function, answer is yes. Suppose you have a sequence of functions fn, each functions fn's are differentiable, fn converges uniformly to f, can I say that f is differentiable? Just think about in the real setting. Now I am asking the same question, since I am dealing with complex valued functions, so that means I know the concept of analyticity. Now I have a sequence of functions fn. I know the meaning of that sequence of functions converges to some functions f uniformly. Now each fn is analytic. Can I say that my limit functions f is analytic? Answer is yes actually. Okay, this is very strong. Maybe next class I'll talk about that. Okay, I think I should stop here. So that's all for today's lecture. In my next lecture, I will start, or I will introduce the notions of power series, because you see, when I will talk about the notions of power series, it involves functions. In fact, it involves the series of functions, series of complex valued functions. That means you have a complex valued functions, then you have a series of those complex valued functions, and then I need to talk about the convergence of that series of functions. So unless and otherwise I do not know the concept of series of functions, then how I can define power series? That is why these kind of concepts are useful to talk about the notions of power series. But to talk about the convergence of series of functions, I need the notions of convergence of sequence of functions. So that is why all concepts are I need those concepts to talk about power series. I think I should stop here. In my next lecture, I'll recall once again this kind of convergence of series of functions, pointwise and uniform, and then I'll go to the notions of power series, and then we'll see a couple of properties of power series. I think I should stop here. Thank you.